The first part is on scaling laws, and the second part is on learning functions.
So I think we can start. Hi everyone. So we're gonna start with our first talk for this afternoon. Please join me in welcoming Jason Lee from Princeton. Jason, the stage is yours.
Hi everyone. So I have a two-part talk. The first part is on scaling laws for SGD learning. The second part is on using transformers to learn function composition. The good thing is if you tune out, the second part is completely independent. So you'll be able to catch up again. This is work with my students, Yunwei Ren and Ishan Nichani. Ishan's on the job market next year, not this year. So save your spots for him next year. And my friend and close collaborator, Denny, who was on, Ishan and Denny were involved in both papers. Denny's right now a postdoc or current instructor at NYU and Flatiron, and I'm Jason at Princeton. Okay, I think everyone's probably seen this kind of picture, starting with hardness, which is a paper by the Baidu quite a while ago now, Kaplan at OpenAI, and then later the Chinchilla paper. Basically, what they found is that if you choose your you balance the compute and the model size and the data all appropriately and take the Pareto frontier. All of these dotted blue lines are different runs they did on some architecture. I think this is from the Kaplan paper. And then they'll find that it fits a power law here. The coefficient is minus 0.05, and that's this Pareto frontier. So this form was from the Chinchilla paper. And their notation, which I won't be using later on, is D is a number of data points and N is parameters. Okay, so the notation is a little weird for us. N to the minus alpha plus N to the minus beta plus C, which you can think of as some Bayes error, some irreducible error. So they kind of found that throughout the last maybe say 5 or 10 years, that this is a pretty reasonable and accurate model of what happens when you double your data size or double your architecture. And they also found in the Chinchilla one that these alpha and betas are pretty close to each other, leading to the so-called Chinchilla optimal scaling for compute. On another sort of a slightly separate line of work is that they found that a lot of these skills that we'll find are emergent. So this started from a paper by Jason Wei, Surya Ganguly, and others, is that you have this sharp emergence of many skills. Is that it looks like you've learned nothing here, and then suddenly it shoots up. This is test error, or test accuracy, sorry. It's sort of, in other words, it's sort of unpredictable scaling in the skill acquisition. It looks very different. These two pictures are very different. One of them is this nice smooth decay, and then one of them is at some emergence time it shoots up. Okay, so kind of what we want to look at is these two phenomenon, is this emergent behavior and skill acquisition and its relation to smooth neural scaling laws. There is a very concrete hypothesis about what's happening here. In two papers from last year, in this additive model, this first one by Michaud et al. Is led by Max Tegmark at MIT, a physicist, and this one is by also a group of physicists at Oxford. And the conjecture they had, which I think OpenAI also frequently mentions in their talk, like Jason Wei, is that the cumulative objective is potentially a sum of these emergent skills with abrupt phase transitions. I'll show you the picture in one slide. And the juxtaposition or the summation of these emergent curves at different timescales relates in the power law. Namely, you add up a lot of these at different shifts and heights, and you might get this. It'll be clear in 1 second. What these papers basically did is then they just said, okay, what if the cumulative loss is a sum of losses and each one has that emergent behavior and the optimization is completely decoupled? This is not usually what we would think of as a loss function. As we usually think of a loss as one architecture minimizing. They modeled it as a bunch of decoupled one where they could control, where each one is just a separate optimization. And they got the picture of, let me find the picture. I'll show you the picture in a second. I should have put it here. Basically, so what I want to point out here is not a single model. It's a bunch of additive models, like indexed by the number of skills, and they're weighted by power law. Yeah, Peter. Think of a skill as one loss function. Like this, like loss. So basically, I'll write what they modeled is like, you can think of their model as loss is the sum over P is 1 to big P. You don't need to. There's a AP here. Think of AP as 1 over P to some beta. Beta is greater between half and 1 to get the curve in chinchilla. And then this one is like, concretely described better, I do it like this. Theta P squared minus theta star P squared. So like the model in these two papers are both essentially this, is that it's completely decoupled optimization. Each of these, I put a square here to get that sigmoidal shape. Instead of if it were a linear model, you don't get the sigmoidal shape. Yeah. And then that model, each individual one will exhibit this. And when you vary the AP, the heights are different, and then time at which they happen shifted according to 1 over AP. So then in that model, it's very easy to show that this picture, the sum of them, decoupled optimization will exhibit this. You can kind of just see each one is this. Imagine that's a Riemann integral, and that's kind of the reasoning chain. Okay, so actually, I'm going to start from a pretty different place. My favorite toy model in the last year or two is this Gaussian single index model, which we really understand the emergence very well in a pretty precise sense. I think many of the audience may already know this, but I'll go over it anyways. So there's a single unknown direction theta. It's a GLM. There's a link function sigma star. And what's important for this talk is you may as well just think of sigma star as a Hermite. It turns out that the only thing that matters is the first non-vanishing Hermite coefficient. So for simplicity, you may as well think about Hermite. And it's known that for the running time emerges at dimension to the power of this k minus 1. So roughly this measures how complicated it is in the exponent. This beautiful work by Ben Arus and his former students basically did this sort of Stein's lemma argument. And you can see this emerges from the gradient, which is theta, the ground truth direction. Just if you kind of Stein's lemma the gradient. And this thing, after Hermite extension, is d to the minus j over 2. You can then just solve an ODE to track the amount of time you needed to grow from this very small number to O of 1. Anyways, the summary of this is that we understand precisely that the number of samples and the emergence time is exactly d to the k minus 1 if you use online SGD or gradient flow. And if you use other algorithms, you can get the optimal exponents here. But for this talk, let's just think k minus 1 is a number in that theta. Okay, so we understand what this is saying is that we understand in this picture, this emergence time is d to the k minus 1 if you have a single index model. Okay, yeah, so you have a plateau that's of length d to the k minus 1, and then you descend quite quickly. In essentially order 1 time, you go from correlation that's very close to 0 to correlation that's 0.99 in this model. I'll get to the relation of how the skills are related. Sorry, single index model becomes a skill later in 5 slides or so. Yeah. Right now, it's just a recap of what a single index model is. Okay, actually right now. Okay, so we're going to look at actually a multi-index model or 2-layer network. The main assumption are these ground truths are orthogonal. And then if you like, you can call this a skill. And the summation, there's a normalization here. The summation of AP squared will be 1. Later on, I'll be showing the way to get the scaling laws to assume they look like this. But for the next 5 minutes, they'll be anything. But they just sum to 1. And the point is now you're learning a sum of single index tasks, but a varying signal strength. And we're going to assume k is bigger than or equal to 3. It turns out 2 and 1 are corner cases. Yeah. And the main point here is that these strengths will then generate different lengths of the plateau in this in that emergence picture. So kind of the setting to keep in mind is we want to, eventually we're going to derive a scaling law. So we need to think of P as very big. You want that sum to become a Riemann integral. So what that means is that we're going to think of this as like d to some constant, think maybe d to the 0.1. And one challenge is that the condition number is very, very large, is going to be a large polynomial in P. And this is because to cover the power law case. Almost all previous work in this model is exponential in this ratio. So this is one of the major optimization hurdles to handle. And also, we're not going to use layer-wise training because in this scaling law, they're looking at a particular algorithm. So we really wanted to look at SGD without any modifications or massaging. So the algorithm is very vanilla SGD. Yeah, so this work is about the optimization and sample complexity for just online SGD. We're going to be able to tell you exactly the time at which theta p is learned. And then by integrating that, we'll get the scaling law. The student is a homogeneous 2-layer network. So the activation is matched. It's 2 homogeneous. This is motivated by ReLU and also earlier talk. The reason 2 homogeneous is convenient, it's not necessary, but it's convenient because it decouples the learning of the angle and the norm. In 2 homogeneous, you always learn the angle first and then the norm grows. And this is, for example, if you train a 2-layer ReLU network, you train the output layer A's and W's, it will remain 2 homogeneous and always the norm won't grow until the angle is aligned, until the angle you have large dot product with the ground truth. Not absolutely necessary. Any higher homogeneity, I think, should work, but it won't have this perfect decoupling. Yeah, the algorithm is, like I said, is online SGD, 1 sample, process it, and so forth. Yeah, so the main optimization result before I get into the scaling law is assume that the teacher's width is some subpolynomial in D to the 0.1. The learner is over-parameterized by P squared. And then I use online SGD. The learning rate depends on this Peter, yes.
Sorry, I forgot. Sigma for the teacher is the same?
It's matched, yes. Oh, I think I forgot to say one important thing. I think that will help for intuition purposes. For those that have looked at this problem, probably want to think about tensor decomposition. If you integrate over x of f minus f star, actually, this objective, it turns out to look like tensor decomposition. W norm squared. This is the unit vector tensor k minus the teacher. Sorry, this is an M. So in the population level, it looks like tensor decomposition. It's not, this is mostly just for intuition reasons. You can think about this as if you like, as doing gradient flow on an orthogonal tensor decomposition with a square loss. Yeah, so this is the learning rate. It depends on the minimum A you want to learn. We're not going to be tight in any P factors, but it's tight in the D factor. Yeah, so and then basically the alignment for theta P to learn, sorry, there's typo, the teacher was theta P, I guess, is for WP to align with theta P happens exactly at this time. It's 1 over AP and you plug in the learning rate. And this is in fact up to like 1.01 and 0.99, which will turn out to be important later, is to be very sharp in the characterization because you want to integrate it later and you don't want like 2 times across each other too much. And this is the total running time. This matches what Ben Arush did for a single index model. That's the K-1. We're not tight on these. Okay, how this compares to prior work. A lot of the prior work that uses like, this is a paper by Yuanzi Li and Tang Ma in Cold, very difficult to understand, but at the end of the day, the conclusion is exponential in the ratio. And they modify the algorithm. They're doing some truncated gradient descent. This paper by Kazu Sato, who is a student here, I don't see him, and Denny, they also can only handle logarithmically many neurons. So it's very hard to integrate that to get a scaling law because it's exponential in the condition number. So the technical challenge is 1, characterizing the sharp times, and 2, handling this exponential issue, because this will always kill you if you want to look at scaling law when things are decreasing. There were also a lot of papers from Rong's group, this Kazu Sato's paper, my own work, which involves like reinitializing the algorithm. Like basically you train for a while in phases and then you reinitialize the ones that you think are stuck, and then you train for a while longer, or you impose a manifold optimization. These all can kind of work and they all handle various aspects, but all of them, they lose something in the sense that they're not tight on this exact time, or the algorithm is significantly different. Anyway, so we provide a sharp characterization of each theta P in this tensor decomposition or online SGD. Okay, so I should have put this picture earlier. Okay, so let me explain this picture. This is the smooth neural law that like in Chinchilla or Kaplan. These are the single index learning curves or emergence. And then this is like the time 1 emergence, time 2, and so forth. And then now we're going to make the power law assumption. We're going to take our previous result and specialize it to power law and see what happens. And what it says is that now the learning rate times time emerges at p to the beta. That's exactly here. And you merge here. So each of these is p to the beta for different p's. And then the population mean squared error, if you integrate these, like, when you've learned one, you drop by a squared. Like if I learn a1, my loss drops by a1 squared. So you can just integrate how much you drop by and you'll get this power law. This is sort of the Riemann sum becoming the integral thing. And this is the cumulative loss. Andre.
The task losses are inner products or something? Like, is that what you mean by like, is that, I guess, what the green and the blue curves are for?
The task.
Like, what is the task? The loss of the task? Is it the inner product?
It's, yeah. It's exactly one term here. It's basically W bar, which is the inner product to the kth power or something. Minus with the norm. It's exactly this squared. So it's like 1 minus the inner product to some large power. Yeah. But it reaches 0 super fast. That's the other kind of important thing. 1 second. Yeah. So yeah, it's learned at exactly this time. The mean squared error is basically, if you're smaller than the time to learn that neuron, you pay it in the loss. And if you're bigger, it's 0. And then this time is super short. because like the time of the in-between is super short. And then that's how you get this p to the 1 minus 2 beta, is you just simply integrate this characterization. And then do some change of variables. T maps onto the like which one you learned in some one-to-one bijection. Okay, there's something really tricky about the discretization, which got me, at least me, for a long time. Actually, before I was trying to illustrate everything in continuous time, and it's super misleading in this problem. In this problem, it's not a linear function of the optimization variable. So it's very, very misleading to think of the time as running time or even samples. Like I was trained to always think of, if you have gradient flow, probably if you're not doing anything super wacky, you can think of it as gradient descent is that rate, and then online SGD is that rate, and then online SGD has a sample complexity. So there's like a formulaic way to go from gradient flow to sample complexity. And then I did that by eyeballing this, and then I remembered my statistics training from graduate school. I'm like, whoa, this contradicts the minimax rate for weak LP balls in Johnstone's book, or Donahoe and Johnstone in McGibbon, and so forth. And then I was scratching my head for a long time. And then my students are too young, so they don't know any minimax. But anyway, I had me confused. And this is the trick. Basically, there's a correct step size to use for the pth task. The correct step size to use, let's say I know predetermined I'm going to run for this long, or I only want to learn up to the pth one. You should set it proportional to a to the p, or p to the minus beta. And now this one learns at n is p beta, but then this guy depends on the beta, right? Because there's a beta here. So that becomes a 2 beta. And now you recover, this is the minimax rate for this weak LP ball or the LP ball. And now it matches. Without this, you didn't have the 2 here, which was too good to be true. It's faster than the minimax. Yeah. So there is something tricky here. Don't always interpret gradient flow as immediately sample complexity. Although the discretizing, you cannot discretize as a constant rate here, because the smallest signal, it depends on how long you want to learn. And then it's like the smallest one. If you set eta bigger than the A, you'll never learn like A min. If it's bigger than A min, it's like you've given up on A min. Yeah, so the correct thing to do is set the learning rate like this, or use a decreasing learning rate at the appropriate schedule, and then your rate will look like this. And that's the right minimax thing. Okay, so I was very happy. Okay, let me say like 2 words about the proof sketch. Yeah. Basically, the proof is, if you've worked a lot on like power method or tensor power iteration, a lot of what I'm saying might sound familiar. Basically, the whole game in optimization for tensors is to know like which student goes to which teacher, and hope that and be able to guess that from the initialization. So here, this is like this initial overlap. You just look at this dot product the teacher. It turns out that there's a nice decoupling because of the overparameterization, is that when all of these are small, this is kind of intuitive. When everything is small, the square loss does not cause things to couple. And it's as if it's just single losses. It's as if the equation I erased, where it was the sum of losses, not the norm squared of a sum. Like you can kind of pull the sum out. And then things are decoupled. And then the overparameterization allows you to be able to predict which student learns which teacher. And that one grows very quickly. But everything else remains small when that single one is learned. And then when you're learned, because it's square loss, you have this automatic deflation. His transition is very sharp. He learns like, that's this curve, this time here, like he goes like here, here. And this time from here to here is super short. So then after he's done and his loss is 0, he doesn't affect anyone else. So implicitly, everything decouples. And this is kind of what happens in the gradient flow. When you do the online SGD, there's sort of a standard recipe, like I was saying. There's a bunch of martingale tools. And from our earlier work, we developed some refined version of these martingale tools. And you have to use this unstable discretization, meaning you choose a learning rate to determine what is the lowest one you're going to not give up on. And everything else there, you're actually unstable in those directions, but you've given up on them. And that's what's happening roughly in this proof. Yeah, and we do have, oh yeah, Jingfeng, yeah.
So when you say the unstable ones, does it like exponentially diverge, or what happens over there?
It turns out no, they're unstable in that you can never learn them, but they never blow up. Their gradients are very close to 0 because their A's are so small. It doesn't cause divergence, yeah, because they contribute to the loss in such a small way. There is one thing that we have a big gap on. If you remember the empirical literature on scaling laws, people always talk about at least 2 parameters, and I've only talked about 1. The 1 parameter I talked about was samples and time, and they're kind of the same in the online SGD. But the other one is model size or width in this case, and I've kind of given up on that. The correct answer is very easy. You just take your thing and you truncate that, the number of neurons you have, you'll get this, and this is obviously the right answer, I think, and it should look like this. What we're able to prove now is a factor of 2 off, because we need to over-parameterize by this to achieve some sort of decoupling. So you can see we're paying like a half here. So it's a worse rate on the width, although I think we eventually will solve it, but it's not super easy, I think. Yeah, so the time scaling is right, the width scaling is off right now. Yeah.
That is an upper bound.
This is an up. This is like this is an upper. You should interpret this as an upper bound. I believe it's loose. Yeah.
And the conjectural scaling law, you believe it's like a.
I believe it's tight, but it's just from adding 2 things together, right?
Okay.
It's because like at this width, the optimization might fail, but if it didn't fail, it has to look like this, right? Because this is the statistical minimax rate. This is the obvious approximation rate, so it has to look like this. Yeah. Yeah. So.
Is it possible to make the initialization smaller? In this case, the interaction between the neuron is not active. Neuron can be smaller.
We're already using that. Yeah, we're already setting the initialization. The initialization is small enough so there's some initial decoupling.
So why you need M is larger than P?
Right. So if you don't have M large, you'll have a phenomenon is that one student will be he will be the most correlated with 2 different teachers. For example, you have 2 things and then one is 45 degrees. So he is maximally correlated with E1, theta 1 and theta 2, and you don't know which one he goes to. I mean, he goes to a bisector and he should split, but this is difficult.
Is it possible to set the dimension is much larger than dimension much larger than everything? So by the initialization, all the initialization is like orthogonal. So basically
but this doesn't depend on the size. It's already normalized. It's only about the angle.
I mean, if the angle is orthogonal and you assume your teacher's angle is randomized and generate and your initialization is also like randomized, so all things should be like orthogonal with each other. Why it can be matched? Why can one neuron can be matched for 2 the teacher neurons?
It's sort of like, just imagine you have a bunch of chi random variables, right? The angle. It's sort of like, or the absolute value is chi's. Then it's sort of like just it's possible like, and then you have think of a matrix. This matrix is like indexed by teachers here and students here. But just because you got unlucky, it might be like this is, and if your M is equal to P, this will certainly happen. It turns out M equal P squared, this never happens. And in between, I think it does happen, but there should be a more subtle optimization way to handle it. I think it cannot be handled through probability. It's really, the dynamics should somehow still work out, but yeah. I think it's probably, if there is an argument, it should be dynamical. That's my guess, I guess. But yeah. Yeah, so there should be, some other, here, typically in linear regression, for example, with Jingfeng and Li Cong, we had a paper, and Peter and Sham, we had to work on linear regression where it was 2-parameter power law, source and capacity conditions. Here we didn't do that. The reason is because it messes up the norm in the Hermite. And we figured out that you need to change the algorithm to project onto ellipses. And then you can do something, but it feels not natural. And more interesting, I think, would be for compositional generalization is when learning skill 3 required knowing learning skill 1 and 2, then how does 3 emerge after skill 1 and 2? Here, all the skills are like, they're not hierarchical nature. Probably this requires 3 layered networks. Yeah. Any question? I think this is my last slide for part 1. Yeah.
So regarding the learning rate thing again, so if I understood correctly, the fact, so you said you have like some of the tasks that are dropped because basically they are too sharp, and so you have this large learning rate. Yeah. Right. But at the same time, they have like a small contribution, so things don't blow up. So do you think, how specific is this structure where tasks, like sharp tasks, have also a small contribution? Like, is it really related to your setup, or do you think it's like general?
I think it is the trend in practice. You decay your learning rate throughout, right? Because like, if you don't decay your learning rate, there's like there was from loss 1 to loss half, you can use a much bigger learning rate from than half to 0. I think decaying your learning rate is a real thing, I think. But I don't know. I mean, I don't think the generative model is particularly realistic, but I think roughly matches the idea of decaying learning rate. Yeah, that's it.
For the last page in this part, for the last page.
Oh yeah, here. So you say like the scaling laws from compositional generalization. Is it possible to just think like you have a sum of sparse parity, and for the leap competitive paper you learn the loss is like you have a plateau and a decrease and a plateau and a decrease, and this is like you learn the scales.
I think it's possible. But maybe let's take that offline. I think that's getting really into the weeds.
You need at least 3. Is that what you said?
Greater than equal 3. 2 is a corner case because it's not identifiable. Yeah. I think the same things hold for like subspace recovery. It's just, part 2, you can wake up completely different talk. This is led by my students Zixuan Wang and again Ishan Ichani, with many collaborators, Alberto Bietti at Flatiron, Alex Damian, my student also Daniel, and Denny. Yeah. It's about learning compositional functions with transformers. Let me check my time. Yeah, so I mean, last year, 24 was all about reasoning, right? Like starting from 01 preview, and like every day we hear about benchmarks on math and question answering, coding, whatever. So kind of my goal is to look at a very toy model that has like some semblance to reasoning or multi-step reasoning. Let me sort of explain here what I mean by like the kind of toy function composition I'll look at. Let's say the prompt is John is in the playground, blah, blah, blah. Helen is playing with John. Helen picked up the football. Where is the football? And then, of course, in the playground. But there were many things you had to compose together to get this answer. You had the location, was the playground. He's with Helen, and he's holding a football. So you're kind of composing together different functions, and you get playground as the answer. You can think of this as these were inputs to the function, and then also with football were the inputs, and then this, and then you get an answer. So you compose together a bunch of functions that is specified in the input or the prompt. Okay, we're going to model this. This model is not the most natural, I think, but we're going to model this as where you have some hidden functions that you don't observe. These functions, the inputs are permutations, sigma 1 through k and x. And then the function is hidden, but it depends in a way both on a latent unobserved quantity and on sigma 1. So the reason there's a latent unobserved quantity is there's going to be a statistical lower bound, so something needs to be unknown. If these were just sigma 1, it would be fully observed and it would only be a computational task. So we made it a little bit harder by making, so like for example, concretely, this function will be another permutation. You just need to compose an unseen permutation pi1 with sigma 1. I feel like I'm running low on time. There's some motivation from chain of thought. The way I think about it is chain of thought is in the input you have composition, right? And we know from much theoretical work, Ziyuan's paper, for example, that this is very expressive. I forgot the formal circuit complexity, like TC0 complete, I think. But you need K inference up. You're chaining together many calls, and it's potentially inefficient for very simple tasks. Without chain of thought, we know it's kind of not as good, this situation, but it might be much faster. And I want to look like what kind of functions you can compose internally, meaning that can it just be done with one transformer, not invoking the transformer K times like in chain of thought. And more importantly, can you learn composition efficiently with just gradient descent? Okay, self-attention. This is a self-attention block. Is Matus here? I have no MLPs again. I know I'll be criticized, but it's simple self-attention, softmax. And there's KQ and OV. The KQ is combined into one matrix. The OV is one matrix. Also, no MLPs again. Yeah, we're going to look at, again, attention-only transformers, but they're going to be deep. That's the main innovation here. So we know from previous literature on expressivity, for example, this beautiful paper by Bing and some work by Matus and Daniel, that they can compose functions internally, at least as long as they're parallelizable computations. So composing K functions only requires log K layers, not naively K layers. So it requires depth, but not a ton of depth, okay? So for example, this K-hop induction task by Clayton, Matus, and Daniel, these automata, these are all tasks that need log K depth. And I'll explain how our thing relates to this in 1 minute. So we're looking at this task we call K-fold composition. It's very similar to that K-hop task. The concrete task is there's some latent permutations pi1 and some observed permutations sigma. You give in an X and all of these, your input is X and all the sigmas. And your goal is to compute this. This function, you can check, requires at least log K. And it's not too hard to show expressivity at log K. And again, we have these latents just to make it a valid statistical problem. So there's some unobserved quantities. Let me quickly talk about the expressivity. We're going to look at powers of 2 because it's just cleaner. And then you're going to need 1 plus log K layers with this embedding dimension. Big N is the size of the universe of X's to express K-fold composition. The idea is not too complicated, though. It's very ugly to write down, kind of like in all of these expressivity. Kind of the idea is that the first layer will encode the pi's. And then after the first layer, your output will be sigma 1 composed with pi 1, sigma 2 composed with pi 2. And then I have this notation hop. Hop is basically like the simplest building block. So hop I2 is something you express with a depth 2 transformer. It's pi I, sigma I plus 1, sigma I plus 1. And then we're going to recursively compose this. And the point is that once you can compute the hop at 2, you compose 2 of them, and you'll get hop at 4. And this is kind of illustrating why you only need log K depth. Because if you have function composition, you first learn how to compose half of it, then 1/2, then you recurse on the other half and other half, and you compose them, and you only need log. Yeah, Andre.
Just make sure I'm tracking. So the class capital F gets hidden in the constants or something. Like you just assume the base element is expressible by some like constant size transformer.
This one. Yeah. That's in this K and because that's why we use permutations. Yeah, to be So there's no it's the base class is easy, right? And this is very analogous to the Bing's paper and Daniel, Matus, and Clayton's paper. So this is not really any contribution here. But you do have to, I guess we should stare at it a little, because if you want to understand how optimization might work. So basically, if you open up the attention layers, everything is one hot here. The one hot embeddings, the key query is going to have ij is going to point to I pi of j. And then the value matrix copies this quantity into the residual stream. So now you'll have hop I1. So the first layer, at the end, you'll have this thing, which is the one hop. So this is the base case to get one hop. And then you compose two of these and you'll get two hop. Okay. And then this is the induction step or recursion step. Once you have hop at 2 to the L minus 1, you attend to I plus 2 to the L minus 1, you attend to hop I, hop J, I think this should be like up here, 2 to the L minus 1. And then the value matrix makes in the residual stream. And then finally, the next layer reads it, and you compose two of them, and you get this. These are really annoying to read, but it's not, I think it's very easy if you try to write it down. Okay, so the question is this, it's nice, you can kind of construct anything kind of, but whether it's actually learnable, especially by GD. There's a simple, quite simple negative result in SQ lower bound is that, I'm not going to explain the XQ model, but basically it says that if I gave you gradients that were slightly corrupted by 1 over root n, it asks whether it's still learnable. So you can think of gradient descent as in with adversarial noise is kind of an SQ. If you squint, maybe SGD is. But anyways, what this says is that your number of queries needs to be n to the power of k. It's exponential in k. Or you just need a super small tolerance. But anyways, either of these translates into a large number of samples to get loss. You like this is you know, like all SQ, it's a little heuristic, but it largely probably suggests there's some hardness here. Okay, so how do we get around this hardness? We have two strategies. The first one is less realistic, but easier to understand. The second one I think is quite realistic. I'll tell you the easy one first, is you just do this in steps. Just like the architecture was constructed recursively. You first train on very short hops. You first try to learn hop 1, then you learn hop 2, then you learn hop 4. And then once you've learned hop 4, you can learn 8 and so forth. And you can learn now it takes poly of n and k samples. So sort of the upper bound is it's some polynomial. These aren't sharp for sure. You can learn epsilon approximates this k-fold composition function. So I guess it's kind of indicating this intermediate supervision makes it much easier. This may remind you of like, let me kind of explain what the curriculum is doing. Like when you learn hop 1, you're just learning ij attends to this. This is super easy. Then when you learn this, once it gets this attention pattern, to learn the next one, its input is already like this now. And then you just have to learn to compose two of these together. So each one of these is quite simple to learn. And each one of these is analogous to learning a single induction head, roughly speaking. Yeah, Andre.
Are the lower layers frozen when you get to stage L?
Yes, yes. Like the architecture is a single architecture. And you can train all of them. It doesn't really matter. But you train a different readout for the length, because otherwise you don't know the length you're outputting. Yeah. What was I saying? Yeah. Okay, in practice, people don't really like curriculum learning because you need to like curate the data to make it increasing difficulty. There's some issues of forgetting the earlier ones. Much more common in practice is the practice of using mixture. Some hard problems, some easy problems. This is very easy. Like if you look at the DeepSeek V3 or R1, all of them talk about having some hard, some easy problems. So what does that correspond to here? We're just going to have some data with long compositions and some with short compositions, some with k equals 2, some with 4. And we're just going to throw it all into a loss function and train the whole transformer with this loss of like different data lengths. Again, in polynomial in K and N, big N, if you just throw on this mixture of data, you will also learn the K-fold. And let me say like a few words about intuition. The proof is really very similar technically to the curriculum one. What happens is that if layer L isn't learned yet, the gradients of the later layers of like L prime bigger than L, they're really close to 0. So they're not even moving. It's like if you see a data point with and it has 1024 hops, 1024 composition, its gradient is just going to be 0 until you learn the 512, the 256, and so forth. So it's as if gradient descent implicitly has a curriculum. On the first pass of gradient descent, it's only going to learn the 1 hops. Then after it learns the 1 hops, it learns the 2 hops, and then the 4 hops, and then the 8 hops. And then once it learns the 8 hops, all of those are like just frozen, the gradients are 0, and the 16 will be non-zero, but the 32 is still 0. And it just proceeds like this. So it's kind of the mixture implicitly induces the curriculum, which is, yeah.
How does the sample size compare? The bound you have at least?
The bounds we have are the same. The bound is reducing this to a curriculum, basically. It's a reduction. I don't know which is better, actually. I think neither are tight, though.
Without any extra sample size?
No. I think the time might be longer, but they're all polynomial time. We didn't really track it. It's gradient descent on the empirical risk. Yeah.
And it's a full batch.
Yeah, full batch on the ERM. Yeah. Probably the time is worse. I would, yeah. Yeah, and the lower bound's not super hard. It's very analogous to parity or any type of SQ thing. The idea is if you have the way to do the lower bound is you just design families of the latent permutations pi, and you make them close to orthogonal. What does it mean for a permutation to be orthogonal? It's just if two permutations don't map to the same place, they're very dissimilar, orthogonal. So we design a family of n to the k permutations where they all map to only O of 1 common places. And then these are nearly orthogonal. It's mirroring what we know from sparse parity. And that's how we got this SQ lower bound. Yeah, so anyways, it's also similar to the positive results on parity from, I think last year, or maybe even earlier. A lot of the efficient learning for parity, it required curriculum or chain of thought supervision. Basically, you needed labels from every step, not even recursive. It was just every step, I think. One thing more interesting about our problem is that parity can be expressed by a shallow neural net. For this k-fold composition, you really do need depth. So you're training really a deep model to compute this quantity. So it's slightly more interesting in the sense that it really shows that you can train deep models as long as the setup is somewhat correct. That yeah, it's not constant depth anymore. I mean, it's only log, but still. Yeah, a lot more general directions. I think the most interesting for me is when it's not just permutations, then you need to think about how is the transformer or MLP going to be related to the base function class you want to compose. In all optimization results for transformers, you basically need the one-hot embedding. We know from expressiveness, like morally, Johnson, Lindenstrauss, and waving your hands, so like log capital N, for example, should be right. But this causes major issues in optimization. Like maybe your first gradient step is approximately right, but like after a while, I can write down the expressiveness with small embedding, but it really screws up the dynamics and I can't track it if you use a more practical embedding dimension. So yeah, right now, everything I know is for tabular embedding. I think that's all. Here's some references. Oh, sorry, Matus and Daniel Layden's papers cut off. Very important reference. Yeah.
Are there any questions?
Probably like super simple, but like, is there any quick intuition for why the gradients are 0 until like the right layer is learned?
It's sort of like the SQ lower bound. It's just like, it's sort of like, yeah, it's sort of exactly as if like the lower bound is like, it's just, You have no information to learn like k equals 4 when you haven't learned the 2. Like the gradient is just one order smaller, right? It's like it's just like, I mean, the lower bound needs super constant k, but like really you can think of it as like each one separated by like a 1 over n or something. Yeah. 1 over n to the power of 2 to the L. Yeah.
Jason, I want to ask a question about the scaling law result.
Yeah.
So the scaling law, in terms of the compute, is that an upper bound, or you also have a lower bound in?
This term is sharp, like up to the p factors. This term is like there's no way to prove online SGDs faster because of the Donahoe-Johnstone statistical results. Yeah. Is that what you're asking? Or
So
at least for online
for
SGD.
N and D and K, those properties.
It's sharp for N, D, and K, and loose for P. Yeah.
Okay. And the step size, it's like you have a fixed step size scheduler.
Yeah,
There's
that's a
no
good question.
hyperparameter.
Right now, it's a fixed step size scheduler, but what we really want is the anytime rate, which would require decreasing, and we haven't worked that out yet. Right now, it's the rate. If you pre-declare to me, I have this many samples, I tell you, I choose a step size depending on the stopping time. It's not an anytime rate. The anytime rate, like morally, is the same thing, and it's you just set eta equals to AP for the time 1 over AP. If I had to guess, that would be the anytime rate for the scheduler. Yeah, but
So
we haven't proved that one. We only proved the one, with a known stopping time.
Is there any evidence that this step size scheduler is like it's good in some sense?
It's very easy to guess this because it's exactly, I'm just saying, like you set it, the step size, depending on which neuron you want to learn and the time it takes to learn. And I set it exactly equal to that, and then I decrease after I'm done. So like that's kind of the reason to set it that way.
Does it make sense to think about when you have a problem which doesn't have a natural serial structure, but I do a serial kind of prompt? What does the model will do to force out, right? A lot of time you don't have very clean, especially when you leave mathematics and something.
You're thinking
simple.
the chain of thought.
Yeah, chain of thought, right?
Yeah.
But you still have some logical thinking. I'm kind of asking, is there a reasonable specified model with some ingredients of the serial thinking, but it's not as clean as the models you consider?
Yeah, I think, I think like it would be, I think one thing is to think about like general function composition, but it's misspecified and you only specify, and you do have some intermediate supervision,
Right.
but even that is misspecified. And whether this error will propagate.
Whether you have a more like nice degradation,
Yes,
since just go
yes.
wacky.
Yeah, it might, I think it's likely, like without major assumption, it probably should go
You think
crazy.
just go crazy?
I guess, but I think there must be, there's always assumptions. It's just, yeah.
So if there are no other questions, we can thank Jason.
Yes.